equals 2 over 2.
Three-dimensional vector is called the cross product. All right, so I think it's natural, you've probably already heard of or seen that it's natural to introduce a third coordinate called z when we're dealing with the three-dimensional coordinate system. So some of you may have some familiar with the third-dimensional coordinate system. You certainly have a lot of experience with 3 dimensions because you live in such a world. So the way to draw this, typically, there are a couple ways to think about this, is the way it's shown up on the board there in that picture. This is just the first of the, this is like the first octant, the positive, where x, y, and z are all positive. One way to form this might be to think, okay, take my normal x and y axis, like this, and then take the z axis and like stab it into the board. There's z, right? That produces for you the coordinate system. Now, I like to rotate it into the position that is up here, visualized on the board there too. I think a lot of people like to visualize, and myself included, like to think of z as being kind of up. Like x and y is the plane that like we stand on, and z is like how high we are above that plane or something, you know. But there's nothing wrong with picturing it any other correct way. There are actually incorrect ways of doing it. But these are cool. These are both fine. Here's an incorrect way of doing it.
Oh.
Right? Notice that there's no rotation of either of these coordinate systems that produces this.
Wait. No.
If you rotate,
Don't try.
yeah, this breaks math for us. Okay, you could do all of math and physics in this coordinate system, but it's called a left-handed coordinate system, and no one likes you if you do that. Okay, so just ignore, just do this. You know.
Why did they teach us
All at once, you should teach that to elementary school.
Yeah,
well,
like,
let's
is it?
expand
Yes.
that. No, so you're making an excellent point. Let's just jump to 20 dimensions right now, and then we'll have the bases covered, like all the way to college.
Well, I was like,
Makes sense.
Yeah. Was that not a hand this time?
oh no.
Boy, you did it. All of the formulas and things we've done before apply for 3-dimensional vectors, so you can write these down if you like, but it's not unexpected that this would be the magnitude formula for 3-dimensional vectors. Though it's not obvious that would be true, you might need to like do a little sketch and do a little proof if that's the case. But it does nicely extend. The dot product is exactly what we would expect. The angle between formula remains the same angle between formula. Yay! And certainly in 3 dimensions, we still have an idea of what it means for 2 vectors to have like an angle between them. If we jump up to like the 4th dimension or something, now maybe that's not as meaningful. But certainly in 3 dimensions, can we still talk about the angle between 2 vectors? Absolutely, and it's still the same formula. So everything you know and love is still true. The new unit vector in the z direction we'll call k. So now we're ready, right guys? We can do it all now. Everything, so on the next slide I just have us like kind of practicing some of these things with 3-dimensional vectors just for the sake of it. Yeah, that's just somewhere down the hall. All right, so anyone still need a second? You still do, I can tell. Okay. Sorry, my page. I want to pull this up in 3D. I've got this beautiful thing we're doing. Look at. It's going to be so great. Ah, there we go. And you guys can do this too. We'll visualize this in a minute. I got an applet to show us in 3 dimensions how these things look. If that doesn't sound exciting, I don't know what does. Yes. I see a hand. What's up?
So if we see a coefficient on k, is that like how we would expand it like we would with I and j?
Yeah, so now I is 1, 0, 0. J is 0,
Okay.
1, 0. and k is 0, 0, 1. And so you could write three-dimensional vector instead of like 3, comma 2, comma 1. You could write it as 3i plus 2, whatever I said, 2j plus 1k or something. It is good to practice visualizing these things. Some of you are like, the hardest part of doing this note taking right now is you're like trying to draw some of these pictures. If you want to picture a point in 3 dimensions, just like in elementary school, when you did like, you know, the very first time when you ever plotted a point, you were like, maybe did something like that.
Yeah.
Where you like put it at the corner of a rectangle.
I still do it.
Okay. Well, if you wanted to plot the point like 3, 2, 1 in 3 dimensions, you might still do the same kind of thing. It's just not at the corner of a rectangle. It'd be like in this picture, it'd be at the corner of a box, right? So on the x-axis, 1, 2, 3, 1, 2. On the y-axis, 1, and then you can draw a box here. This takes skill. Here we go. Vertical, vertical, vertical.
Whoa. Oh.
Right? And now you can see pretty clearly where the point 3, 2, 1 is, yeah? And in some sense, it's actually not, like, in elementary school, you're like, okay, that's just kind of cute, it's cosmetic, but once we get rid of those, like, we still can see exactly where everyone means by 3, 2. Whereas here, if we remove the box, it's actually not obvious unless you label it where that green point is because of our lack of depth perception. Like, same thing here. If you remove the box here, you can't really tell where that point is. You know, it could be way back behind somewhere else. You can't tell. But that's the problem with, you know, trying to visualize 3 dimensions when you only have a screen. All right, so try a couple of these operations. We'll call on 3 people randomly here in a minute to answer these. So just, you know, the point is here not to blow your minds here, it's just to like practice. Can you do this with stuff, the same kinds of questions we've been doing all along? With 3 coordinates instead? Yes. Here's the answer. And let me pull up.
We have like 10 minutes worth. Oh my God, slow down. Oh, hey, this actually. Exactly.
Wait a second. Wait a second.
I got 9.
No, get a vector.
What is that?
Wait, that's all you want.
How's it going?
Oh wait, so you're logging
It's going great. I have a beautiful thing to show you in a minute, but we'll answer these questions and then we'll.
I got ortho.
Oh, I get.
All right. So who's going to answer these questions? Okay. How about we're.
Heaven's right there.
Hi, Kevin.
Kevin, what do you get for the first one? Agree, class?
I feel like heaven's better than like
The Nash. B.
Okay, I got the second one that's orthogonal.
You got the dot product is equal to 0 for the orthogonal? That's pretty exciting, okay? And what does it look like? I'm so glad you asked. That's the one I typed in. Actually, where do I? What did you get for? Did you get this one yet? Take it. We'll give you a second to do that. We'll ask you. So do head minus tail. Do B minus A.
Oh, yes. What are you talking about, Elizabeth? It was last week. That was so.
B minus A.
Show me like definitions.
When you have it, actually, let me know. Let us know.
Thursday.
Yeah, quiz Thursday.
If there's a cancellation, we're still gonna have to quiz Thursday, right? We're gonna do that. that thing we did last Sunday? Or on the,
Yeah, I think we could still have it. I mean, it's on the homework. It's everything up to the guys.
oh,
We're
that's
not
right.
gonna have the review and
Tomorrow's not a review day, so we have another lesson tomorrow.
wait, is it
All right, Ashley, what'd you get? Did you get it yet? No, not yet. So you're doing B minus A, people out there, right? B minus A. I know it's been a little while since we did this, but like, when was that? Friday?
You're right.
Thursday?
It's like AB, the arrows pointing at
So you're doing B minus A, so take each coordinate and subtract carefully.
Square root or cube? Oh, square root. For magnitude square root.
Oh, square root. Square root. So, Ashley, what'd you get? 131. Root 131. What's the vector you've got? Negative. What'd you say? Yes? Okay. And the square root of 131, anyone else? Okay. All right. I'm so glad, Dinesh, that you asked about the visualization of this. I hold this up here. So this is B. These are the two vectors on B. Here's the X. Do you see the X and Y coordinate? The X and Y plane. And then up from that is the Z axis. So you can see here that the second vector drops below the plane. And is it clear that they're orthogonal? It may not be obvious until we like find a good view.
Whoa. Oh, dang.
They do look orthogonal, even though they're kind of like floating in space there, right?
Straight.
Hey, look, which ones are orthogonal? Oh wait, no, that's round. That's round times.
That's orthogonal.
Anyway, you get the idea. You can do this yourself, by the way, now or tonight or whatever. Just go to, just even in your browser on your phone or something, you just go to geogebra.org
I would think in real life.
/3D. You can download the app, or you can say, no, I'd rather just do it in the browser. It works great in the browser. I'm just using my browser right now. So you can do this. You can do this in the browser just as easily as well. On your phone, it works great, honestly. The thing I typed in is don't disregard. Just don't look at all this stuff. I just typed in vector and then right, the two vectors. That's all you need to do. I put all this other stuff in here just for fun. Like here, I have this vector floating there, and I made sliders so that A, B, and B and C could be controlled. This is the X and the Y and the Z component, right? And then I also decided the thing I wanted to plot was K times the vector, where K is equal to a number of your choice. So we can actually see the scalar at work here. Oops.
Oh no.
Wow.
The scalar did not make it spin 3.
Oh, I don't know why.
All right. Yeah, so we can make it, right now the K is like 1.04, but obviously we can make K be
It's getting longer.
or negative.
Oh my god, it's negative.
Isn't that exciting?
Yeah.
Why were you calling me back and forth?
You can do all of this from the comfort of your own phone too, if you want. You can change it.
That's weird. Round with
There you go. Now it goes up to 10, just for you, Brandon.
the monumental day by entity. Which way does it even go?
Bye, vector. Bye, vector. Oh, wait, there it is. All right. Oh, everyone look at my cute daughters. Oh. Thank you.
I recently changed that.
I did recently.
Hey, why didn't you do anything? Heart rate.
All right, let's talk about the cross product. Okay.
Yeah.
All right. So the things we've already talked about today, even though it's cool to be thinking about the third dimension, nothing really has been a huge surprise so far. This is something interesting to talk about because it's a way of multiplying two vectors, or multiplying. that only works in 3 dimensions, and it's only works and is only meaningful in 3 dimensions. Doesn't work in 2 or 4 dimensions. Only works in 3 dimensions. Okay. Now, I think we were trying to be careful with our language the other day when we did the dot product yesterday. Right? The dot product is A dot B. So we're actually going to use the dot to mean the dot product, and we're actually going to use the cross right here, this symbol, to mean the cross product. And make sure you're clear that for vectors, those mean different things, even though in your normal life in multiplication, we've used those interchangeably for years. So for vectors, we need to be careful which one we mean. So the cross product is a way of multiplying 2 vectors and producing a 3rd vector, and I'll show you how to do this. Okay? Now, I know you haven't yet, and we will in this unit encounter a concept called the determinant, and when we're doing matrices. Maybe you've seen determinants before.
Oh no!
But this, calm down, it's fine, everything's fine. Okay. But this symbol here, these vertical bars around this matrix mean take the determinant of this matrix, and I'll show you how to do that with this 3 by 3 matrix. Okay. It doesn't matter. I'm gonna everything's fine. Anytime I'm here. Okay. I'll hold your hand. Everything's gonna be fine. So the way you do this, I'm gonna teach this from a pretty procedural perspective here to start with. You load in I, J, and K, which is a little weird to do this, but those are the unit vectors obviously in the X, Y, and Z direction. Then you load in order your components from A and your components from B. Okay? And then, to take the determinant of a 3 by 3 matrix, in general, here's how it goes. And I have some highlighting that's going to help you see this. Now each of these is another determinant of a 2 by 2 matrix. Now which 2 by 2 matrices are we talking about? For I, it's this. Sometimes in linear algebra we call this the minor matrix over here, right? So it's I times the matrix formed by the other parts of the matrix that aren't in its row and column. Do you see that? And then it's J times the part of this matrix that isn't shared in the same row and column as J. Does it make sense? And then it's K times the determinant of this matrix. Right? I'll do this again. Right? So I times the determinant of this matrix. J times the determinant of this matrix, that is cross off the row and column that J is in, and you've got your matrix. And then K times the matrix, the determinant of the matrix that's not in the row and column that K is in. Now, there's one other snag, and that's that this minus is not a typo, right? So it's this thing times I minus this thing times J plus this thing times K. And I know that's a little bit of voodoo right now, but we'll just go with it. It will actually, it won't get bigger. Right. But for us, right. But if you wanted to take a 4x4, it would go back to minus. It would be a minus and then plus. And actually, there are more things you could say here. In linear algebra, if you take that course, you'll do some determinants. You'll discover, for example, that taking the determinant, there's nothing special about going across the first row and doing what we're doing. You could go across the second row and block off the parts and you'd get the same answer in the end. Or you go down a column and do this, and it would work too. But we'll just go with going across the top row and multiply I times J times, even though there are actually lots of nice ways to do this. All right, now this also requires that you remember how to take a 2 by 2 determinant, but maybe you do, right? Diagonal minus diagonal, right? So it would be let's make sure we have those ideas and this picture in our head rather than memorizing this formula, because you'll be like, okay, is it A2, B1? No, it's B3 minus C. No, there's no C. No, wait. There's a B2. How about you just remember that it's, the picture here, okay? And someone told me last period that there's a typo here. One of these subscripts. It was supposed to be a B2 or something, right? A1, B2, and A2. All right, I think it's corrected now. So now you might be thinking, is this worth doing? Is this this sounds crazy. Is this important for anything? Well, the most important property that we'll take advantage of the cross product in this class is the fact that the cross product gives you a third vector. You take your 2 vectors, and it will always give you a third vector that is orthogonal to both of the original two vectors. And in 3 dimensions, that is always possible, right? You form 2 vectors, and then the third, you can always find a third vector that is perpendicular to both of the other two. Can you imagine that happening? Okay.
Oh, yeah.
Excellent.
Its magnitude also has important meaning, which maybe I'll describe here in a second. So you can see, here's the picture, A, B, and then purple, A cross B. You'll also notice that there's something else interesting in this diagram. It turns out that this is an example of an operation, and there are others in mathematics, that is not commutative. If you do B cross A, you get almost the same answer. You get the opposite. The vector you get is still perpendicular, so it'll work, but it'll point in the opposite direction as A cross B. Here's the picture as an animation. I think this is worth seeing because it's going to help you see what the magnitude means as well. So notice here, when is the cross product, the green vector is the cross product of the blue and the red. When is it at its longest? When the blue and red are, when they're perpendicular at 90 degrees, the green cross product, and they're the shortest, it's a blank 0 when they're pointed in the same direction or in opposite directions, 0 or 180 degrees. So this does feel a little bit like it has some relationship to the dot product. The dot product had those kinds of things we just talked about, except what? Switched, right? So I'll just tell you right now, the magnitude of the cross product of U and V, the magnitude of the dot product was this, right? Wasn't that the dot product? Turns out the magnitude of the cross product is this. What will it be?
Sine theta.
Right, and so you can see that that's kind of capturing what we just said there. The magnitude is not something we'll talk a lot about in this class, but I just thought I'd mention that because you're seeing that in this picture, that it's maximized when they're at 90 degrees. Cross product will come up again a lot in a physics course where you think about angular momentum or electricity and magnetism are 90 degrees to each other. We think there are lots of nice things that we won't take the time to go here because I'd like to make sure we do an example of calculating one of these, but feel free when you're in the comfort of your own home to try a cross product applet. What it will do is allow you to kind of drag the vectors around and do this, right, if you want. All right, let's actually try doing our first cross product together. Here we go.
Try it.
Yay. So we got 3, -1, 2, -1, 0, 4. So we'll do this nice and slow this first time. Eventually you might get faster or maybe even be able to do it in your head. That's fine. Or large parts of it in your head at least. That's a J, sorry. So J is going to be what? 3, 2, -1, 4? And K will be 3, -1, -1, 0, right? Are you clear on where I got all the numbers from up there?
Yes, I am. Oh my God.
Notice at no point am I being like, okay, now B2 times A1 is, right? I don't want to think that way about this. I just want to think visually. And then each of these determinants is something I think you've computed before, right? So -4 times, we have to be careful here. -1 times 4 is -4. Minus 0 is -4i. See, we're almost done. Careful in the middle. What do we have? 12 minus -2, positive 14. Oh, wait, but I told you because you trusted me that it's minus always, so that'll be a minus 14j in the middle. And then down here we got what? 0 minus 1. Yes? If you multiply the two diagonals, you get a 0 and a 1. So 0 minus 1 is -1. Okay, so you could leave your answer that way, or you could write it in the way maybe some of you are more used to. I don't know. Just like that. So we do in fact get another vector, a third vector, and then now verify that this is in fact orthogonal to both of the original two, if you will, because I promised on the last slide that it would be. So can you verify that that's true? How would you do that? Yeah, we can use what we learned yesterday. Yeah, form the dot product of this vector with this one. and this one with this one, and can you just check that in both cases you get 0? We won't write it up here, but someone just verify that it works. That will be at least a check on whether we did this correctly. Just do it in your head even. You check them both? Did you? Anyone else check them? Take the dot product of one of the two original vectors with this one. Did it work? You're just going to trust her? Huh? What's that? 0 and -4. Yeah, so -4 and 0. Subtract. -4 minus 0. Or here, 12 minus -2. Yeah, this and then minus that. I have. Are you prepared for the? Are you prepared for the jokes? Here we go. What do you cross a rooster and a what do you get if you cross a rooster and a duck?
Cross product.
A bird that gets up at the crack of dawn.
Wait.
What do you get when you cross a cow and a chicken?
Ground beef. Wait, no.
A vector orthogonal to the cow and the chicken. Right? 'Cause that's what you. Right? Come on, this is good stuff. What do you get when you cross a mountain climber and a mosquito?
Bug bite.
A mosquito.
No, you can't cross a scalar and a vector. Vector is the thing that carries diseases. I'm told. It's on my biology.
I was right. I said it even before Mr. Chip
Oh
said
yeah,
it.
vector is because it was the thing that just carries that carries the No, we literally
All right, on the homework tonight, guys. On the homework tonight, this is the homework sheet doesn't have any book. You, listen. The book homework. There's no book homework. This is the homework. Why don't you just do the odds? If you want to do the evens as well, that's fine. I think if you just do the odds, you get the idea. Okay. Does it say to do them all?
It says on the back.
Oh, you can whatever it says. It doesn't say to do them all. Okay? Yeah, you don't need to do them all. Yeah, the homework sheet suggests that you only do certain problems, so obey that. It's good for you. See you tomorrow, guys.
I watched that scene.
This is u.b or that is exactly right. This is u cross b. It's not u cross b, it's a match. But yeah, you only have that's a little bit of a lie.